One of the things that I definitely want to do, and I hope this will be a lot of fun, is do some actual, in my field we call it wet lab. Do you call it wet lab when you're actually?
We call it breaking shit. We call it breaking shit.
Okay, we're going to break some.
We break some shit. Yeah. And now I want to say something. My students learn better when I shut up and they break my stuff. And my classes are about 80% hands-on, so they break a lot of stuff. So I'm always repairing things. So
all right, well, we're probably going to break some stuff here for sure.
So I'm in my zone.
But what I want to do is do this with a particular focus. One of the things, and I have to say there's two people that really I must credit this for. One of them is definitely you, and the other one is one of my viewers who I know is watching, and he may be screaming at his monitor too, possibly, but that would be Terry, of course, who I've learned just a ton from. But as a result of what I've learned, and as I've started to become much more comfortable with electrical and apply this, it's really changed the way I do things. One of the biggest things that I have changed in my approach, I am no longer in any way whatsoever a fan of measuring resistance in circuits and on wires. I do not like doing that at all. And I have adopted to instead measuring voltage drop. And one of the things, would you agree that it's probably a good, for the most part?
Well, no, yeah. I mean, the ohm meter has its place, but people don't understand that it was designed to work on a bench with 3 volts. I mean, it's not designed to go 100 feet down a wire on a coal truck. It's not what it's designed to do. So it's going to fail, just by design. The other problem is it takes time, right? I mean, so one of the biggest complaints we've discussed here is that I got to make money. I don't have time to do all this. Well, do you really want to find the 2 ends of the connector that you don't want to go to the end of the connector and find the connector and put a jumper wire in to jump the wire to the other end of the connector and the other end of the wire and then measure an ohm meter? It takes you 45 minutes to do a 15-second test with no results.
Yeah.
That's what makes people upset about electrical. I just wasted all this time and I didn't find anything out. And that's part of the psychology of this.
Yeah.
I mean, so yeah, anything you can do to speed up, and voltage is definitely going to be faster than ohms.
Yeah, and also in my experience, at least, what really changed me is when I consistently found that I did not measure any resistance in a circuit, but then when the circuit is loaded, it's a whole different story, and I can only detect that through the voltage drop, right? That's happened more times than I can count, to the point that to me a resistance measurement is useless to me.
Yeah.
But given that, the point of it is that I can do that because I have an understanding of the concept of voltage drop. So it means something to me. If people don't understand voltage drop, in my opinion, they are at such a marked disadvantage. The things that I can do because of understanding voltage drop, I can tell if there is parasitic amperage in a circuit by measuring voltage drop on a fuse. I can just go to the fuse box and see if there is parasitic draw when I'm chasing a problem, looking at the fuse, because I understand the concept. So what I want to do is I want to do kind of a wet lab thing, but first I'm hoping that you'll do some of your famous drawings and explain to people the concept of voltage drop. And then we've got a whole bunch of electrical toys here from my collection that I'm going to let you run free with, and we're going to give some actual real live demonstrations of voltage drops and some mistakes that most people make, and boy, I know I did, in trying to measure voltage in circuits and resistance in circuits, and why voltage drop is such an important concept.
Can I throw one thing in about resistance?
Absolutely.
Okay. I want everybody to understand that this whole big picture of mine comes down to realizing that the time you spend during the diagnosis is time well spent, because I'll ask guys in class, I teach a lot of truck mechanics, what size socket do you use to take a steer tire off a truck? And everybody says 33 millimeter. And then I say, and what's the average resistance of a 12 ohm AC clutch? Crickets. Dead silence, because nobody knows, because nobody cares. But it's 4. 4 ohms is the nominal resistance of an AC clutch in a 12 volt system in everything you work on, right? Well, now, as you're talking about resistance, guys have a tendency to blow off small numbers.
Right.
But what will 2 ohms do to a 4 ohm component? It's going to destroy it.
Yeah, totally.
So a guy sees the 2 ohms, but he goes, that's nothing, and he goes off somewhere else. So it's not just a matter of knowing how to use the tool, but knowing what to expect. And a lot of times people don't have a genuine appreciation for what is good or bad.
Absolutely.
And they don't learn that because they don't stop and pay attention during the actual diagnostic process. The process is the key, and that means paying attention to the details. By the way, all the left pages in my book are blank for a reason, to write things down.
Yeah.
Right? So if you write stuff down, you're going to remember them. I don't know why the ground wire on a U.S. Army Oshkosh Hemet, the wire number is 1435, but I do, because I've trained myself to think that way, right? Well, if you train yourself to think that way, then these things will be there for you to draw from when you're doing it again. But if you don't ever do that, you don't know. So just it's important for you to think about what you're really seeing when you see it, and how does it really apply. Guys don't generally do that. They're just boom, 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 got to get it done, got to get it done, got to get it done, right? So, you know, and everybody's certainly smart. You're all smart enough to do it. It's not a question of that.
Yeah.
It's just a question of being willing to take the time. So,
yep.
all right,
well,
so
we're going to take the time to do that because
let's break stuff.
Yeah, understanding voltage drop changed my approach to almost everything in a much better way. It's also given me more versatility to do things in a much easier way. So I'm going to let you do what you do best and do those amazing drawings.
All right, so Matt has asked me to use my most potent weapon in the classroom. When I first started 30 years ago, there were no projectors, and now there are no whiteboards. So it's a bad thing. I have to actually include in my contract 4x6 whiteboard, because otherwise, if I get there, there won't be one. So what I'm going to show you guys, real simply, is this idea of the notion of voltage drop, okay? And there's a component of math to it if you care, but you don't need to care. But the numbers do add up, and there are a couple of things you need to know. First of all, getting back to the schematic reading discussion, there's only one load per circuit. All right, so I teach voltage drop as if it was horsepower. And it technically is, in a way, horsepower. Which means if you've got one thing in the circuit, for example, this motor we're going to eventually start doing stuff with, if this is the only thing in the circuit, which is true, then it will use 100% of the horsepower, and in our case, that's voltage, right? So when the engine's running, 14.5 volts, plus or minus a little bit, this fan will be running on 14 volts. Well, that's what it's designed to do, because it says VA07AP12-C-31S 12 volts, okay? I have no idea what any of that means, but 12 volts means 12 volts, right? So this is a 12 volt fan. It needs 12 volts to work, okay? Well, how do we get it there? Through the wire. So if I draw a basic circuit, which is every circuit on the planet, I draw a straight line. There's my voltage, there's my ground. There's the motor. Somewhere there's a switch. Don't care. So if this motor is running normally, then it's going to use 100% of all of the voltage. Now the problem is, mechanically, as we know, you can't get into the motor easily when the motor's plugged in, right? But if we were to put the voltmeter there, and if we were to put the voltmeter here, oops, there, then I should be reading simple numbers, 12 volts. And everything's working great, okay? Now, here's the problem. I get a rusty ground. Something in the ground gets all corroded and grungy. Or the switch contacts burn because motors have coils. Coils make arcs. Arcs burn points. By the way, relays don't burn up. Whatever they're switching burns them up. They don't just randomly fail. So a burned up relay is an indication of a bigger fault in something else. So if I've got green junk in the ground, I can't see 12 volts here. I might only see 2 volts at the motor because the ground is using up 10 volts. Well, one of the most important rules to learn is that plus that always has to equal that.
Kirchhoff's law, right?
And that's Kirchhoff's law, right? Now, if we again think about this as horsepower, then this ground, which is corroded, is robbing the motor of horsepower, which makes the motor go slowly, okay? So it shows up as a failed motor. Now, to confound the problem, as soon as we take the motor out, we can't see that because now the meter reads 12 volts. And every one of you knows that when something fails and you read normal system voltage, your first thought is, I have a failed motor because I have a good circuit. Well, just FYI, the word good means nothing in electricity. There's no meaning to the word good, okay? So it's either failed or it's not failed, all right? And it can only fail in 3 ways: open, short to ground, high resistance. Well, in this case, this is high resistance. Now, the problem is trusting a tool which gives you this number without taking this into consideration means that you're going to replace a motor when it's not the motor, right? And you've all been there and done that, right? Everything's good, I feel great, I read the voltage, I got a good circuit, the motor's not running, I need a new motor, replace the motor, it still doesn't work. We've all been there, okay? So we'll do a little grunge work here on the bench, and I'll explain with real-time meter reading what's actually happening, because Matt has sufficient amounts of junk here that we can build some pretty impressive stuff.
So guys, what we're going to do now, if you saw my last video, we worked on a Jeep that had a blower motor problem, and I explained how the blower motor circuit works, not as well as what Dan would have been able to draw for sure. But what Dan's going to do here is he's going to recreate an actual blower motor circuit that we would have where you can select the speed of a fan. And this should be familiar to you guys that just saw my last video. So Dan, why don't you walk through what you're doing here?
Oh, okay. Well, am I in here? Okay.
Yeah.
Okay. So real simple. Resistors in series add up. So this is a 1 ohm and a 0.47. So in total, we'll have 1.5 roughly. And the standard way that an older non-electronic PWM blower fan would work we would just be simply selecting different resistor positions on the switch. So those of you old enough to remember, a lot of vehicles had that plastic resistor pack that went in the ducting to keep it cool, and everybody said it's all burned up. So I have no idea what's about to happen here, but we'll see, because if I take the fan and run the fan at full speed, that's just straight up 12 volts. Now let's run it through 1 ohm, which I would encourage you.
So you're basically going between the resistors because the current path will go through the resistor, and this one is not in play.
Yeah, because it's just out here kind of hanging out. So so we would go click from high speed to click to lower speed to click.
It won't even run.
It won't even run.
And that's only an ohm and a half.
1.5 ohms.
Yeah, that's amazing, because you're under the impression that you need a lot more resistance, and I will tell you.
And let me demonstrate something here that I teach in class. Everybody gets all keen on this continuity buzzer, and I just want to point out that it's beeping on nothing. But here's the 1 ohm resistor that shut down the fan.
It still beeps.
Here's the 1.5 ohms that shut down the fan.
Yeah, so it doesn't beep at the 1.5.
Yeah, but it'll beep on the 1.
But on the 1, it beeps, making you think, oh, I've got full continuity there.
Yeah.
And you have an ohm of resistance, which is enough.
It's enough.
And even just a half an ohm more. And that's what's kind of interesting.
Little things matter.
Yeah. Well, that's pretty lucky for you, Dan. But
30 years of practice though, Matt, come on.
So one of the things, by the way, that last video I did with the Jeep where we did this, and I took out that resistor pack, I was kind of curious just how much resistance is there in these systems, because I'm well familiar with how they work. And I was blown away when I measured the resistance at each step. It's like less than half an ohm.
Not a lot.
It's not a lot.
No.
It's not a lot. And you just add up, like just an ohm, and that moves the fan from the highest speed setting to barely moving.
Yeah, and just for giggles, the Load Pro with a 1 ohm fault shows a drop of a half a volt, and that's mathematic. So if it drops a half a volt, there's 1 ohm of corrosion. I mean, it's Ohm's law. Ohm's law math is perfect, and any number that is less than full system voltage indicates something. You just have to be wise enough to understand how much is good and how much is bad. But I would point out that we wouldn't be there if it wasn't broken. So if it's broken enough for us to be there, it's going to be broken enough to find. And we've had this tool out there for over 25 years, and it works. It does the one thing it's designed to do, and it does it very well. That's it.
So Dan, one question that I think a lot of people will have, I remember, because hopefully you guys are familiar enough with this, that you know how it works. Basically, what's going on is there's obviously some kind of internal resistor in there that you're measuring across. Yeah, you're measuring the voltage drop when you're introducing another resistor. And we've talked about, like on the 5-volt reference circuits, how in the PCM you're going to have an internal resistor, and then that variable resistor that is actually the component, the potentiometer or whatever, you have to read between those, because otherwise you would read either 5 volts or none, right? So, but I remember reading a review on Amazon of this, and somebody trashed your review because they said, if you look at the device here, I'm trying to say this without laughing, there's no way to replace the battery. And I would hope that you guys watching would know there is no battery in here. But you may also be curious, how is it loading the circuit? What's the trick with it? And you're willing to share with what the mechanism is.
Well, the simple answer is that as soon as you unplug the motor, current flow stops, and we don't care which direction it's moving, but it stops. Mm-hmm. And when it stops, mathematically, there's no voltage drop, because voltage drop equals amps times ohm, so there has to be amperage or current for a drop to show up. So all the tool does is it just is a substitute load. So when you take the motor out, this set of leads becomes the motor. It becomes the ECM. It becomes the light bar. It becomes the backup alarm. It becomes the blower fan, because we don't want to damage wiring as best we can avoid it. So by removing the connector and simply reading the voltage at the component, again, we're doing a continuity test. And if we see voltage, we don't have an open or short, we load the circuit. If the voltage doesn't drop, we buy a motor. But if it's any other reading than that, we know that we have a circuit failure, and we want to repair the circuit. But it's fairly straightforward. So
would you be able to draw it on your?
Yeah, sure.
Yeah,
sure.
Let's draw that so you guys can really understand, because this is such an important concept to understand. So let's let Dan do his magic here.
Okay. So Matt wants me to show you this, and I'm just going to be very honest with you, guys. The patent was issued in 2002. It expired in 99 because it was filed in 99, and I had 20 years and it's done. So reality is that the patent is actually not even valid anymore. But there was a patent, and I did sue someone for stealing it. So just FYI, okay? So if you take your meter and put your meter into the system where the connector for the component is, right there, and right here, then we're going to read source voltage. Well, this source voltage reading only tells me that I don't have an open circuit and I don't have a short to ground. That's all it's telling me. That's not broken, and that's not blown. That's what that number means. That's what the number means, okay? That's all it means. So saying, I got 12 volts is not a diagnostic answer. I don't have an open or short, that's a diagnostic answer, okay? So what's going on here? Well, if we put corrosion in the circuit somewhere, that's a resistor symbol, and that's green crap. So there's green crap in the wire through a connector or something. I don't know, I'm making this up, right? But that is problematic because, as you just saw, it's still going to read system voltage. Because there's no current flow because we have an open circuit, this meter on volts does not complete the circuit, okay? So what do? Well, we put a switch in the circuit with a resistor. So now when we turn the switch on, that's now the load, and it should be dropping 100% because that's how voltage drop works with the only load in the circuit. That's in the way though, so the voltage drops because this plus this equals that. Simple. So yeah. So that's how it works. And I didn't invent Kirchhoff's law. I didn't invent voltage drop. I just invented the tool. So when you load the circuit, by pushing this button, you're turning the circuit back on, because without the circuit functioning, you won't read a voltage drop. You just read voltage. And that's all it does.